Welcome back to ECE 442-542. This is a video for Unit 5's homework, which is homework number 5, and these are supposed to be hints to help with working homework number 5. Problems 1 and 2, I'm going to be talking about designing a desired closed-loop transfer function T sub c of z to meet the design specs. Problem 3, in one sentence, I've basically assumed that you're using a zero-order hold equivalent of the original unstable system. And problem 4 will look at addressing the different Ragazzini restrictions or which ones apply, etc. in problem number 4. If you're trying to remember what it is that we're looking at in the first two homework problems for homework number 5, you're being asked to design two-pole system transfer functions. That's this T sub c of z that you're being asked to create in problems 1 and 2. Really nothing beyond that. You're just being asked now to create a T sub c of z, and you're not asked to find a controller. You're just being asked, how do you find this T sub c of z? And while we're here, problem 3 is designing a stabilizing controller. The system G of S has a unstable pole. The pole is at S equal to +1, and now you're also asked or told you could design your closed loop transfer function to exhibit deadbeat response. And remember, deadbeat response is you have all of your poles at z equal 0 or at the origin. And finally, problem 4 is design a Ragazzini controller to produce a deadbeat response. So your T sub c of z will have a denominator that's just z raised to some power. You're trying to find all of your dominant poles, or you're trying to locate all of your dominant poles to produce a deadbeat response, which is to locate them all at the origin for this particular system, which is a stable system, but you can actually see that it does have an unstable 0, and that 0 is at 1.1. In problem then, or in problems 1 and 2, let me see if I can somehow get my tablet to respond. Here we're wanting T sub c of z, and it's being told go ahead and locate your 0 at the origin. That means our numerator, if our denominator is second order, we're going to have 1 0 at the origin. That's the z, and then we could have a yet to be determined gain constant k, and the denominator is now some second order polynomial, z squared plus alpha 1z plus alpha sub 0. We are now wanting to find alpha 1 and alpha 0 based on the performance specifications. For background, this is really working from lectures 1 and 2 and the supplement number 1 for lecture 5.2. Remember that our settling time specification in terms of breakfast cereal shapes, that's circles. We have these concentric circles, and the settling time spec impacts the radius. The smaller the circle, the faster the system, or the shorter length of time for a settling time. And the settling time specification could be specified in terms of the number of samples. That's what I'm referring to as capital N set. But it could also be specified in terms of an actual time given by capital T subset or capital T settling time. And that's in terms of so many sample periods. So if you know the sample period, capital T, and you know the actual value of your settling time, T subset, you can now solve for the number of sample periods to get you to meet that design specification. Once you have n subset, capital N subset, you can use this expression or this equation to solve for the number of samples to get you the 1% settling time that you desire, or what is the radius that will accomplish that capital N set when raised to that number of sample periods, that R raised to that number of sample periods to produce a number less than 0.01. So we solve that for R, and now we have some real circle the answer type questions. A shorter settling time means larger or smaller circle around the origin in the z-plane. If we want our settling time to be smaller, shorter, then we actually are wanting for a circle, we want a smaller radius circle around the origin in the z-plane. That smaller r then corresponds to a shorter settling time, which produces a slower or faster response. If we have a shorter settling time, that then says that we have a faster response. Translating that then into the z-plane, we could now draw two circles, concentric circles, and they each have complex conjugate poles. Those are represented by the triangles here in this diagram, associated with poles that are a certain distance, r sub 1 or r sub 2, away from the origin. Here you can hopefully see that the red circle is inside the blue circle. We're assuming that both of these circles are inside the unit circle, or otherwise we wouldn't have settling time. We would have an exponentially growing response. So now we're assuming then that these circles are inside the unit circle. The poles associated with r sub 2 produce, since they're on a smaller circle, a faster response versus the poles on the circle determined by the radius r sub 1. So those, if you're interested in settling time, then you're looking at these concentric circles. If you have percent overshoot, now that's going to be these logarithmic spirals, and where do they potentially intersect or overlap with the circles, and that might give you an indication as to where to locate your desired poles. So if they simultaneously satisfied those specifications, then you would have just the intersection point resulting from the percent overshoot, logarithmic spiral or heart shape, and these circles. If you had a peak time spec, then you're looking at particular angles where the larger angle corresponds to a faster response or a quicker to the peak behavior. Problem 3, that's basically then what you need, I think, hint-wise or help-wise to address problems 1 and 2. And there are several different desired transfer functions that you're being asked to generate. Now you're in problems 3 and 4 actually going to be solving for a controller. So now we are wanting to find this capital C of z, and in the first problem, problem number 3, we're trying to stabilize a system that was g of s equaling, so here g of s was unstable to begin with, and we're now trying to stabilize it. I'm assuming you're using a zero order hold equivalent because this is now what you're trying to control with capital C of z. And you want to now incorporate, this is scenario number 2, you're incorporating the dynamic behavior of the zero order hold together with the plant G of S and this sampler, this A to D conversion sampler on the back end. Now you have G of Z. Well, you can now find the Z transform of G of S over S. Now you're looking to find 1 over S, S minus 1. If you can find that in a row in this Laplace Z transform table, you could then immediately write down what this expression produces. If you wanted to, and you wanted to say, well, let me do that in Matlab, you could. Here's the original system. G of S is 1 over S minus 1, and that's what you put into MATLAB's C2d. So we need to now translate this system into an object, a transfer function based object in MATLAB. The numerator is 1, that's the first argument. The second argument is something bigger than a constant. It's now a polynomial. Here's your S to the 1 coefficient. Here's your S to the 0 coefficient in that vector. And this is a row vector. If it was a higher order polynomial, you would just keep growing that higher, or coefficients associated with higher powers of S, to the left in that. So if you now had something like S squared plus 4S plus 5, that would then be a 1 for the highest or leading coefficient, a 4 for the linear coefficient, and a 5 for the constant coefficient. That's how you would then translate polynomials into row vectors in MATLAB. And that's what I'm trying to indicate here. Here's the denominator, S minus 1. That now produces, together with the numerator, with this transfer function, it produces 1 over S minus 1. If you now want the zero order hold equivalent, you can produce that by using the C2d function in Matlab. We've now created the continuous time system object, G, together with the sample period, which is given as 0.2. That's the second argument, and if you close the parenthesis and only include 2 arguments in C2d, the default is to produce the zero order hold equivalent. And that will then produce this particular transfer function, capital G of Z, with a constant numerator and a denominator first order Z minus 1.1. And notice that that denominator in G of Z does possess a root outside the unit circle. We do have an unstable an unstable system, G of Z, that's consistent with our unstable plant in the continuous time setting. The pole zero excess, we have a first order polynomial in the denominator, a zeroth order polynomial in the numerator. We now have a pole zero excess of 1, which is also consistent with our original system, capital G of S. You're wanting a deadbeat response. Well, maybe you say, let's not increase the order of my desired transfer function, closed loop transfer function. And we want maybe a deadbeat response. My denominator then is just Z, or a factor Z minus 0. And I just am saying, well, I had a first order here. Can I achieve what I need using a first order closed loop transfer function? That means I don't want any polynomial of Z other than a constant in the numerator. And can I now achieve what I need by just assuming this transfer function, capital T sub C of Z? Problem 4. Now you're given a system that actually has let me not get ahead of myself. G of Z has a pole zero excess of, how many poles do you have? You actually have 2. If you now had something like that, you would have 3 poles. If in fact you had that was a 2 and this was a 3, then you would have 5 poles. Here we have a quadratic, 2 poles. That's the highest power of z in the denominator. That's the number of poles. We have one, or a first order numerator polynomial. We then take the difference between the number of poles and the number of zeros. That's 2 minus 1, or 1, for our pole zero excess. If that's the case, then restriction 1 says we can't ask our controller to do the impossible, which says that we need the desired closed-loop transfer function, t sub c of z. It must have a pole zero excess at least as large as g of z. So in this case, we need t sub c of z to have a pole zero excess of at least 1. It could be 2, it could be 3, but you might as well start with 1 and see if you can accomplish what's needed without too complicated or too complex of a desired closed-loop transfer function, t sub c of z. G of z has an unstable, and now we can go back. You're comparing zeros and poles, their locations, to the unit circle, and hopefully you can see that g of z has an unstable 0, and that now tells us that we need to worry about restriction 2. And restriction 2 says that we need to retain this factor in our t sub c of z expression. So now that is immediately inserted in t sub c of z. We can now introduce another variable in the numerator, a k, which could be determined, and we wanted a deadbeat response. We need t sub c of z to have a pole zero excess of at least 1. That means the denominator needs to be at least second order, since our numerator right now is first order. And can we now accomplish what we need? Now we have one remaining parameter that's yet to be determined. That's the k. We've already located our poles. They're at 1. They're at the origin. We have our unstable 0 factor preserved based on restriction 2. Now we can use k as a design parameter. And one of the ways that we could maybe design for a behavior that we want is we might want a DC gain of 1, and that would then allow us to have 0 error due to constant inputs. Or if I applied a 4 as my reference input, my output would go to 4 in the steady state. So after the transients have dissipated, my output would be 4, and I would have 0 error between the output and what I applied at the input. That should get you hopefully moving more quickly towards the end result of producing solutions for homework number 5.